Welcome to the module on input analysis and modeling. This is the first video where we'll talk about the introductory material and define what we mean by input analysis and modeling, and it will be followed by several additional videos where we talk about particular tasks. Basically, input analysis and modeling involves two distinct functions. There's an analysis function where we are trying to determine simulation inputs based on our system at hand, and then there's a separate modeling task where we're learning to generate observations, or we're creating computer models so that we can generate observations of the input models. So if we go back and think about um, our basic simulation modeling process, we have some system that we are creating a simulation model of. Simulation model. And the basic idea is that we want to make decisions from our simulation model that would apply to the system that we're modeling. And as we'll see, the simulation model is comprised of a set of inputs in addition to the structure of the model itself, and generates a set of outputs So the input modeling and analysis task basically is to understand how the system behaves and extracting from that the data that we need to model the simulation inputs, and then creating the computer code or computer models that generate observations of the corresponding random variables. So let's look at a simple example, and we're going to use the automated teller machine model, model 4.3 from the Kelton et al. Book. And in this model, basically we have customers that arrive to the system, enter through the entrance, they walk to the ATM, they either perform their transaction, either withdraw money or deposit money, and then they walk out. And so we have a simul model of this right here, model 4.3. Let me just jump to the simul model. And here we have it. And so basically the input analysis task associated with this model is to determine the corresponding input functions for our model. In particular, we have three elements that we're interested in for this model. We have the customer arrival process, we have the ATM transaction times, and finally we have the time that it takes customers to walk, both from the entrance to the ATM and from the ATM to the exit. Vincent describes the input modeling process. This is from the Handbook on Simulation chapter by Vincent, as follows, as shown in this figure. We basically have some available resources that we use to create our models. We have some prior experience, we have some theory, and we potentially have some data. And this is all based on some real-world process. And remember that we have a system here that's shown under real-world process, and our objective is to create the input model for our simulation. And to do that, we rely on these three basic resources, and we have two different types of assessments. First, we have a validity assessment where we're trying to ensure that our model, the model that we create, is a valid representation of the real world process. And then secondly, we have a reasonableness assessment, which is essentially determining or ensuring that we have appropriated a reasonable amount of resources, is one way to think about it, in developing this input model. So to further define this notion of a reasonableness assessment, clearly we could collect lots and lots and lots of data. If we think about the arrival process in particular, we could collect lots and lots and lots and lots of data about the real world customer arrival process. And in some sense, the more data we collect, the better our model would be. On the other hand, data collection of that form is expensive. We have to have someone that's actually collecting that data, and therefore at some point it becomes unreasonable. And the thing to keep in mind through our modeling process is this creation of a simulation model involves several layers of abstraction. So when we create the system, the simulation model, we're abstracting the system. When we interpret the simulation outputs, we are then doing a second abstraction when we apply those outputs. We apply the analysis to the underlying system. So with that notion in mind of abstraction, creating the input models, our objective is not necessarily to create a perfect input model. Instead, our objective is to create an abstract model that will answer the questions that we have. So for example, going back to our ATM model, maybe the purpose of creating the model is to decide, would I rather have one fast ATM or two slower ATMs, and try to make that decision based on customer experience, utilization, and so forth. And so our objective from an input analysis standpoint is to identify these components, the customer arrival process, the ATM transaction times, and the walk times, and create appropriate models so that the decision I make, whether it's one fast ATM or two slow ATMs, would be correct or would be representative of what we would see in the real world. So back to our computer model, when we create customer arrivals in our simulation, essentially what we're doing is we are creating these individual observations. And so let's focus on the customer arrival process and the service time and ignore walk times for just a minute. And we can see that we are creating these observations of random variables. So the y values here are inner arrival times that are created, and the t values are service times for the corresponding entity. So each entity, when we think about entity 3, for example, has a corresponding inner arrival time and a corresponding service time. And when those two values are used in the simulation model, they execute in this case, the single server queuing logic. So in this case, t and y are both discrete time stochastic processes because we have the observations of the random variables. And the first step of the input analysis process is to understand and to define or to model these discrete time stochastic processes for the ATM system that we're modeling in this example. So looking in a little more detail at the stochastic processes, we see that we can represent the process this way, Sn, where n is the index, in our case the time index. So for our example, the in arrival times and the service time, then the n value would be a customer number. So customer 0 or customer 1, customer 2, customer 3, and so on would be the n value. Now each one of these Sn is an occurrence of the same phenomenon. In our case, it's either an in arrival time or it's a service time, and there's a corresponding probability distribution associated with each one of these occurrences. Now we're going to focus exclusively, almost exclusively anyway, on something called an IID process, or an independent identically distributed process, which has the following characteristics as defined or is described in Vincent. First, all of the Sn random variables are probabilistically independent of one another. So in our case, knowing one in arrival time or one y value doesn't give you any information about another subsequent y values. Similarly, knowing a y value doesn't give you any information about the corresponding t values. The second thing is that under the IID assumption is that all of the random variables follow the same probability distribution, so they're said to be identically distributed. So this notion of independent identically distributed has the two characteristics of independence and identical distribution. Going back to our ATM example, we see that the in arrival times are modeled with a property on the source object, and the service times are modeled with a property on the server object. And so in our case, this IID, the IID assumptions is what let us use the random exponential property for the in arrival times and the random triangular ABC for the service time process. And so back in our model, we see that. So there's the inter-arrival time property here, and the service time or processing time property here. And so these observations are created as IID observations. And so what this statement, what this expression, the semio expression, random.exponential 1.25, says sample an observation of a random variate that's exponentially distributed with a mean value of 1.25. And so this expression generates IID samples. And so it's important that the underlying model, or that the system that we're modeling, has these same IID properties, because the default values that we use, or the default mechanisms we use to generate observations, generate IID values. And so in this case, the input analysis and modeling task is to first identify that, in this case, the inter-arrival times are exponentially distributed with a particular mean, beta, and that the service times are follow a triangular distribution, and then we use Semio's built-in functions for creating that model. So the analysis is to identify the distributions, and then the modeling component basically involves using Semio's default properties. So that concludes the introductory video in this module. The next steps that we'll do is we'll look at fitting distributions using observed data, where we'll assume that we have some observations of these, for example, inter-arrival times and service times, and we fit the distribution. Then we'll look at using Semio's input parameter properties, and finally we will finalize the video, this module, talking about one slight deviation from the IID assumption called a non-stationary arrival process.